Nernst equation. This Nernst equation, we use it to determine the or for the calculation of the EMF of galvanic cell. To determine the EMF of a galvanic cell. What is this Nernst equation and how do we get it? As we know, as we told that the very basic principle of galvanic cell is that free energy change of a chemical reaction is converted into electric work. So, if you have a reaction in which the free energy change is delta G, then we said that delta G is equal to minus NF E cell, where E cell is the EMF of the galvanic cell. Delta G is the free energy of the reaction. That means, suppose if you have a reaction A plus B gives C plus D, like for example, Zn plus Cu2 plus gives Zn2 plus Cu, like this you have. This will have certain delta G. Then what is the EMF of in that galvanic cell? So, for that we give this relation delta G is equal to minus NFE. Then also here we have something called standard free energy. Standard free energy delta G naught. When delta G is equal to minus NFE cell, delta G naught is equal to minus NF E naught cell, where E naught is said to be standard reduction potential. Standard reduction potential of an electrode. Every electrode under standard conditions has assigned certain particular EMF, certain value, that is what we call standard reduction potential. Regarding that, after this Nernst equation, we will have a detailed discussion. But for the time being, just you take that E naught is standard reduction potential, delta G naught is minus NF E naught, where delta G naught is standard Gibbs free energy. The standard Gibbs energy is nothing but the free energy change involved when the reaction is taking place in standard conditions. What are standard conditions? The reactants involved are of having unit active mass, that is 1 molar solutions, or the gases are taken at a pressure of 1 atmosphere under standard conditions. Temperature is 298 Kelvin, pressure is 1 atmosphere, and the elements or the compounds are present in their standard states. So, delta G naught is equal to minus NF E naught cell. From thermodynamics, from thermodynamic principles, we write that delta G is equal to delta G naught plus RT ln Q, where Q is the reaction coefficient. Where Q is reaction coefficient. At equilibrium of a reaction, you can say that Q is equal to K and delta G is equal to 0. At equilibrium, change in any of the thermodynamic properties, either delta S, delta G, delta H, delta U, all are zeros. So, delta G will be 0. At equilibrium, the reaction coefficient is nothing but equilibrium constant K. That K, as here we are considering it the gases and all, if we are considering, then normally what you are supposed to take is Kp, right. Q is equal to K. Therefore, what you can write is from this that delta G naught is equal to minus 2.303 RT log K. Well, this is a different case. Now, delta G is equal to minus NFE, delta G naught is equal to minus NFE naught cell. Therefore, now this is suppose if you consider that this is equation 1, this is equation 2 and this is equation 3. From equations 1, 2 and 3, what you can write is minus NF E cell is equal to minus NF E cell is equal to minus NF E naught cell plus RT ln Q. Minus NF is equal to minus NF E naught plus RT ln Q. Now divide the whole equation with NF minus NF, then what you will get is E is equal to E naught minus RT by NF log Q, or the same thing we write it as E is equal to E naught minus 2.303 RT by NF log Q. This is what we call Nernst equation. So, if you know the standard reduction potential value E naught and Q the reaction coefficient, how do we write Q for this reaction? Q is nothing but active mass of C into active mass of D by active mass of A and active mass of B, which is nothing but we write it as concentration of zinc into active mass of pure solid copper by active mass of copper. Active mass of solid is 1 for copper, similarly active mass for zinc, which is a solid, the active mass is 1. So, we take it as concentration of zinc by concentration of cupric ion. So, this Q is the active mass. Q is equal to, is as we have written, in this case it is. So, this is what you can write is like the oxidized form by reduced form, reduction form. This is another way of writing it. So, finally, E is equal to E naught minus RT by NF log Q, or E is equal to E naught minus 2.303 RT by NF log Q is what we call Nernst equation. So, if you know the active mass and what the number of electrons, this here this N is of course is the number of electrons transferred in the redox reaction. So, the number in the case of zinc copper couple, the number of electrons involved are 2. So, there you can take the value of 2. So, E is equal to E naught minus 2.303 by RT by NF, where N is 2 log Q, that will give you the. So, if you know the concentration of zinc and copper, you can have the value of Q, from which E naught is a standard value that will never change. The significance of E naught, what is E naught and all, as I already told, we will discuss it later. So, E is equal to E naught minus this, and this in fact also we can write it as R value. R is the gas constant, standard condition of temperature of 298 Kelvin if you take, and Faraday's value is 96,500 coulombs, that if you substitute this, in turn you can write it as E is equal to E naught minus 0.059 by N log Q. This is the more simplified form of the Nernst equation. 2.303, R value 8.314, T value 298, F value 96,500. All these values, this whole thing comes out to be, if you substitute, this whole thing will comes out to be 0.059. So, E is equal to E naught minus 0.059 by N log Q. This is the simplest form of Nernst equation. E naught is a constant value. If you know the value of Q, then you can determine the EMF of the galvanic cell. This is the simplest, simple way to remember the Nernst equation. Using the Nernst equation, we can remember the EMF values, and not only the EMF of the galvanic cell. If once you are given the EMF of a galvanic cell, in the case of metal insoluble salts involved in the electrodes, the solubility product of the salt also can be determined. Solubility of the salts can be determined, pressures of the gases can be determined, and the purpose to which the cell can be used also can be determined if once we determine the EMF values using the Nernst equation. Okay. So, in the next we will see what is this standard for different cell reactions, how to write this Nernst equation, and what is standard reduction potential, how to determine that, what is the significance of that we will see now.